Hello there, and welcome to the Midnight Scientist, where curiosity gets cozy and science takes the scenic route to slumber. Tonight's gentle journey is all about one of the most mysterious forces we live by, but barely understand: time. It slips through our fingers, shapes our days, and weaves the very fabric of our lives. As you're settling in, just imagine us for a moment, scattered all across the globe, in different moments, in different time zones, yet we have all arrived here together, in this quiet space, in this unique slice of the clock. If you find this voyage soothing, a gentle way to unwind after a long day, I hope you'll feel welcome in this quiet corner of the world. Your presence here helps this calm reach others who might need a peaceful pause too. And now, there is nothing else you need to do. Simply settle in, slow your thoughts, and let's begin. Because somewhere between seconds and centuries, dreams and daylight, lies the story of time. Time has a funny way of stretching and shrinking, doesn't it? 10 minutes of quiet waiting can feel like an eternity, while an hour spent with a favorite hobby can disappear faster than a fading dream. And yet the clocks tick forward, second after second, minute after minute. So what's going on? The answer begins not with physics, but with your brain. Our perception of time, that internal sense of when things start and end, is surprisingly flexible. Psychologists call it subjective time, and it's heavily influenced by things like attention, emotion, and memory. How you feel about time can be very different from how time is actually passing. Let's start with the quiet oddity of waiting. Imagine a calm waiting room. The walls are a soft, neutral color, and a clock ticks gently in the corner. 5 minutes there can feel like half an hour. That's because when not much is happening, your attention turns inward, and that internal focus makes you more aware of each passing second. Now, compare that to a warm conversation with a friend or getting lost in a good book. In those moments, you're fully engaged and your brain isn't keeping track of time so closely. It's like your mind decides it's busy and there's no need to watch the clock. Before you know it, hours have flown by. This is sometimes called the flow state, a term from a psychologist who studied how our sense of time can fade into the background as we become fully absorbed in the present. The novelty of an experience also plays a role. When you encounter something new, your brain takes extra care to process and store the memory. Later, when you look back, it feels like more time must have passed because there's more mental footage of the event. It's why childhood summers can seem to stretch on forever. Your brain was constantly encountering new things, logging every detail. As we get older and routines set in, our brains get more efficient, the memories are compressed. Emotion plays a part too. Studies suggest that awe and joy can make time feel like it's flying, while fear or worry can seem to slow it down. There's a theory that in intense situations, your brain creates denser memories, giving the illusion that time has stretched. People sometimes report this after a sudden, startling event. It's not that time actually slows down, it's that your brain records more details per second, creating a sort of slow-motion playback in your memory. And then there's boredom. You've heard the phrase, time flies when you're having fun, but the opposite, that time crawls when you're bored, is just as true. Neuroscientists have found that when we're bored, the brain's internal pacemaker becomes more noticeable, making time seem to drag. Even our language shapes how we see time. In English, we talk about time as a resource we spend, save, or run out of. But in some cultures, time isn't seen as a line we move along, but more like a landscape we exist within. It's a quiet reminder that our experience is just one of many. But what about our inner clocks? Surely there is some kind of biological mechanism ticking away. And there is, sort of. We all have something called a circadian rhythm, a 24-hour cycle that helps regulate our sleep and waking. But that's more of a daily timer than a stopwatch. For shorter periods, scientists believe we use a kind of mental timekeeper, a network in the brain that relies on a steady stream of neural pulses. When we estimate how long something takes, we're subconsciously counting those pulses. That said, we're not always good at it. Our time estimations can be very off, especially when we're distracted or emotional. There's even a phenomenon called the return trip effect, where the journey back from somewhere feels shorter than the trip there, even if it takes the exact same amount of time. On the way there, your brain is busy processing new information. On the way back, it already knows the route, so the experience feels faster. And of course, there's the snooze button. Somehow those 9 minutes between alarms can feel shorter than any other 9 minutes in the universe. While there's no hard science on that specific feeling, it's likely another case of our fuzzy internal stopwatch just giving up in the face of incomplete sleep. So, what is time as we experience it? It's not just a number on a clock, it's a feeling, a perception, a trick of memory and attention. It changes with our mood, our age, and even the language we speak. It speeds up with joy, slows down with fear, and sometimes, just sometimes, seems to vanish altogether. And while physics may explain what time is on the grandest scales, if time itself is mysterious, our efforts to measure it are a testament to human ingenuity. From ancient sundials to atomic clocks, we've spent millennia trying to wrangle this invisible force into something we can see and count. Let's drift back to the deep past, when the first timekeepers were not clocks, but the sky. Our ancestors were expert observers of the heavens, the rising and setting of the sun, the phases of the moon, the shifting of the seasons. These were nature's earliest calendars. The ancient Egyptians were among the first to formalize timekeeping. Around 1500 BCE, they built towering obelisks that acted as giant sundials. By tracking the shadow's movement, they could divide daylight into segments. It wasn't exact, but it was enough for farming, prayers, and organizing society. Water clocks came next. Used by the Egyptians and later the Greeks and Chinese, these devices measured time by the steady flow of water from one vessel to another. They were simple, consistent, and could work at night, a big upgrade from sundials. Meanwhile, in Mesoamerica, the Maya developed intricate calendar systems that tracked lunar and solar cycles with astonishing accuracy, measuring spans of time covering thousands of years. But back in Europe, it wasn't until the Middle Ages that mechanical clocks began ticking their way into history. At first, these were large contraptions in church towers, ringing bells at regular intervals to call monks to prayer. You might say monks were the world's first and most serene alarm clock users. A major leap forward came in the 14th century with the invention of the verge escapement, a clever bit of engineering that allowed for a more controlled and regular release of energy. This made smaller, more reliable clocks possible. Eventually, clockmakers added dials and hands so people could see the time, not just hear it toll. From there, the pace of innovation began to tick faster. By the 17th century, the pendulum clock entered the scene thanks to the Dutch scientist Christian Huygens. Pendulum clocks were accurate to within a minute a day, a staggering improvement. The need for even more precise timekeeping became critical during the age of exploration. Sailors needed to know their longitude, which required knowing the exact time at a fixed reference point. This led an English carpenter named John Harrison to invent the marine chronometer, an ultra-precise clock that could survive the rocking of a ship at sea. His invention changed navigation forever. By the 20th century, we entered the age of quartz. Quartz crystals, when subjected to an electric current, vibrate at an incredibly stable frequency. These vibrations were used to keep time with far greater precision than anything. The most accurate time on Earth. You'll have to go atomic. Atomic clocks, first developed in the 1950s, measure time using the natural vibrations of atoms. A cesium atom, for instance, oscillates over 9 billion times per second. That number is now the official definition of a second. These clocks are so precise that if one ran for 100 million years, it would be off by less than a second. Today, atomic clocks synchronize everything from GPS satellites to the internet. Without them, your phone's map wouldn't work, and financial systems would be chaos. Time, once measured by dripping water and sun shadows, now depends on atoms humming like microscopic metronomes. And yet, despite all this precision, time still feels strangely personal. We can divide it into hours, minutes, and seconds, but no matter how finely we slice it, we each live it differently. Maybe we began measuring it to regulate prayer, grow crops, or schedule trade. But maybe, just maybe, it's because humans are deeply comforted by rhythm. The steady beat of time, no matter how elusive, gives shape to our days. It offers order in chaos. A tick, a tock, a tiny whisper from the universe saying, "You're here, now." For most of human history, time was a local affair. But then came Isaac Newton, a 17th century physicist who gave the world a model of the universe that would dominate science for over 2 centuries. In his view, space and time were like a grand, invisible stage on which the drama of the universe unfolded. The actors, planets, apples, cannonballs, moved about, but the stage itself never changed. Time, in this picture, was absolute. It ticked along at a constant rate, everywhere, for everyone, forever. In his own words, it flows equitably, without regard to anything external. In other words, time is like a great silent river, flowing at a steady pace, regardless of whether anyone is watching. This idea made intuitive sense, and it gave scientists a powerful tool. It allowed them to describe motion in precise terms, to synchronize events, to create reliable predictions. For hundreds of years, scientists relied on his absolute time and space to explore the natural world. But as good as Newton's model was, it eventually started to show cracks. In the 19th century, scientists studying light and electromagnetism noticed something strange. Experiments suggested that the speed of light was always the same, no matter how fast you were moving. That didn't make sense in Newton's universe. This problem simmered for a while, until a young patent clerk named Albert Einstein came along. Still, Newton's idea of time as an ever-flowing, universal quantity left a deep imprint. We still speak of time as something we can waste, spend, or save. Our daily schedules run on the belief that time ticks the same for everyone, and in most everyday situations, that's still perfectly true. It's only when we start dealing with very high speeds or very strong gravity that Newton's picture begins to blur. He gave us a vision of a predictable, mechanical universe, running like clockwork. He brought order to the cosmos and made time something we could measure and trust. But time, as we'll see, has more than one personality. If Isaac Newton imagined time as an endless river, Albert Einstein revealed it was more like a vast, flexible fabric. In the early 20th century, Einstein upended our understanding of time with his theory of relativity. Let's begin with special relativity, published in 1905. One of its key ideas is that the speed of light is the same for all observers, no matter how fast they're moving. This leads to one of the strangest consequences imaginable: time dilation. Simply put, the faster you move, the slower time passes for you, relative to someone standing still. If you were to board a spaceship and travel at near light speed, your onboard clock would tick slower than one back on Earth. You would age more slowly. This isn't science fiction. It's been observed. Atomic clocks flown on airplanes have ticked ever so slightly more slowly than their counterparts on the ground. Not enough to notice, but enough to prove that time really does slow down with speed. This leads to the famous twin paradox. Imagine two twins. One boards a spaceship and flies around the galaxy at high speed, while the other stays home. When the traveling twin returns, they will be younger than their sibling, because their time actually passed more slowly. But speed isn't the only thing that can alter time. In 1915, Einstein unveiled general relativity, which revealed that gravity, too, can warp time. General relativity describes gravity not as a force, but as the curvature of space-time caused by mass. The more massive an object, the more it bends the fabric of space-time around it. What this means is that time runs more slowly in stronger gravitational fields. If you stand next to something truly massive, like a black hole, time ticks more slowly for you than for someone farther away. This has also been measured on Earth. A clock at the base of a mountain will tick a tiny bit more slowly than a clock at the top. So technically, your head is aging just a little bit faster than your feet. This phenomenon has real-world consequences. So what does all this mean? Einstein showed us that time isn't an absolute universal river. It's a stretchy fabric, woven together with space itself. It can expand, contract, bend, and twist, depending on speed and gravity. And that means your time, the pace at which you experience the universe, depends on where you are and how you move. Time is no longer the same for everyone, everywhere. It's personal and relational. Einstein's work didn't just rewrite physics, it changed how we see reality itself. Time is not a fixed background, it's part of the dance. Let's imagine, just for a moment, that you wake up one morning to find everything running backwards. Toast leaps out of your mouth. Raindrops fly upward into the sky. Strange, certainly, but according to the laws of physics, not entirely impossible. This leads us to one of the most intriguing questions in science. Why does time seem to have a direction? In most of the fundamental laws of physics, time doesn't really have a preferred direction. They work just as well backwards as they do forwards. And yet, in everyday life, time feels like a one-way street. Eggs break, but don't unbreak. We remember the past, but not the future. So why this disconnect? Enter the concept of the arrow of time. The key to understanding this arrow lies in one of the most important laws of physics, the second law of thermodynamics. This law tells us that in a closed system, like the universe, entropy, or disorder, always increases over time. Things tend to go from tidy to messy. You can scramble an egg, but you can't unscramble it. This tendency toward increasing entropy gives time its arrow. It's why we experience events in a particular sequence. This leads to a deep question. Why was the universe in such a low entropy, orderly state to begin with? The leading theory is that the early universe, just after the Big Bang, was incredibly uniform and smooth. Over billions of years, the universe got clumpier and more chaotic. But why it started that way is still one of physics's biggest open mysteries. There are other arrows of time, too, that all point the same way. There's the psychological arrow. We remember the past, not the future. This is because memories require physical processes in the brain that increase entropy. There's the causal arrow. Causes precede effects. And there's the cosmological arrow, the expansion of the universe itself. The fact that galaxies are moving away from each other gives a sense of direction to the cosmos. All of these arrows, entropy, memory, causality, cosmic expansion, all line up. They all point in the same direction, which is comforting. Time as we experience it is fundamental. Some physicists argue the arrow of time is an emergent phenomenon, something that arises only when we observe the universe. In some interpretations of quantum mechanics, time is just a label for different states. The universe doesn't feel time. We do. And no matter how deeply we dig, time continues to be both incredibly real and maddeningly elusive. If classical physics treats time as a dependable train schedule, then quantum mechanics treats it more like a jazz improvisation, flexible, mysterious, and sometimes hard to follow. Welcome to the quantum world, where reality gets fuzzy and time becomes more of a polite suggestion than a fixed rule. In the classical universe, you can say an object is right there at this exact moment. But in the quantum realm, particles exist as waves of probability, clouds of where they might be. And surprisingly, time doesn't play a starring role here. It mostly shows up as a background parameter, something we plug into the equations to keep things moving. The foundational Schrödinger equation, for example, describes how a quantum system evolves over time. But time in this equation isn't something that bends or stretches. It's just there, a silent spectator, much like in Newton's world. This creates a curious split. But things get even stranger when you try to merge quantum mechanics with general relativity. These two theories are the twin titans of modern physics, but they describe time in completely different ways. Trying to unify them is like trying to choreograph a ballet using the rhythms of the deep ocean. This leads to what physicists call the problem of time. When you try to describe the whole universe quantum mechanically, you find something odd. Time disappears. One of the main equations that pops up in quantum gravity is the Wheeler-DeWitt equation, and it contains no time variable. It describes a universe that is timeless, no past, no future, just an eternal, unchanging now. So, is time real, or is it an illusion? Some physicists believe that time is emergent, not fundamental. Like temperature, an individual molecule doesn't have a temperature, but a group of them does. In the same way, time might emerge from the complex interactions of countless quantum events. Others look to quantum entanglement, the bizarre phenomenon where two particles become linked. Some theories suggest that time itself could arise from the growth of this entanglement throughout the universe. But if time is so shaky at the quantum level, why does it feel so solid to us? We live in a world where countless quantum interactions average out into a smooth, reliable reality. Our brains are hardwired to perceive cause and effect, to string events together into memories, and to imagine futures. We tell stories, and stories need time. So, while your wristwatch may tell you the hour, quantum physics whispers, well, yes, from a certain point of view. Underneath the comforting narrative of your day lies something far more elusive. Time may not be the ticking of a clock, but the unfolding of possibilities, the hum of reality tuning itself ever so slightly with every passing moment. Time isn't just something tracked by clocks or planets. It's also humming quietly inside of you, in your cells, your sleep, your appetite, and even your mood. Your body is running on its own internal clock, and it's a very old one. This is what scientists call the circadian rhythm, from the Latin for about a day. These are the biological processes that follow a roughly 24-hour cycle. They regulate everything from when you feel sleepy to how your body processes food. The master conductor of this orchestra is a tiny region in your brain called the suprachiasmatic nucleus, or SCN. It's located right where it can receive information from your eyes, allowing your body clock to sync up with light. When your eyes detect sunlight in the morning, the SCN gets the memo and sends out signals to adjust hormone levels and body temperature. One of its most important jobs is controlling the release of melatonin, the sleep hormone. Melatonin levels rise in the evening, helping you feel drowsy, and fall in the morning, helping you wake up. It's your body's gentle suggestion that it's time to rest. Interestingly, this internal clock doesn't run on an exact 24-hour cycle. Left on its own, it runs a little bit long. It's daily exposure to light that resets the clock, keeping us in harmony with the Earth's rotation. When this system is disrupted, we feel it. This is the source of jet lag, when your internal clock is out of sync with your new environment. Another modern culprit is artificial light. Before electricity, we were largely guided by the sun. Today, the blue light from screens can trick our brains into thinking it's still daytime, suppressing melatonin and making it harder to fall asleep. Not everyone's rhythm is the same either. Some people are natural morning larks, while others are night owls. This biological time affects your metabolism, your immune system, your mood, and even how you respond to medications. There's a growing field called chronopharmacology, which studies how drug effectiveness changes depending on the time of day. Plants, too, follow these rhythms, opening their leaves to the sun and closing them at night. Animals, from birds to bees, regulate migration and foraging by their internal clocks. All of this paints a picture of life on Earth as deeply intertwined with a biological time, grounded in light and dark, warmth and cold, hunger and rest. A time that pulses through living things like a gentle, ancient drumbeat. So, the next time you feel tired in the afternoon, or unusually alert at night, it's not random, it's rhythm. Your body is dancing to an invisible beat, one that kept our ancestors safe and well rested, long before time zones or digital watches. And while we may try to bend time to our will, deep down, our cells are still following the sun, slowly, quietly, faithfully. Have you ever noticed how time seems to play favorites? A holiday week flies by like a feather in the breeze, but the last few minutes of a task you'd rather not be doing can feel like an eternity. This is psychological time at work, the wonderfully warped way our minds perceive time's passage, which often has very little to do with clocks. Let's start with the familiar feeling. Time flies when you're having fun. This holds up to scrutiny. When we're deeply engaged, our focus is absorbed in the moment, and our brain effectively stops counting the seconds. On the flip side, boredom stretches time. When nothing is engaging us, our brain starts clock watching, and we become hyper-aware of each passing second. There's also the peculiar difference between looking forward to something and looking back on it. A week spent on a novel and exciting trip might seem to fly by in the moment. But looking back, the trip feels long, packed with vivid memories. That's because novel experiences create more mental bookmarks. Contrast that with a routine week. It might have felt slow while you lived it, but in hindsight, it blurs together. Fewer bookmarks, fewer memorable moments, less perceived time. This is part of why time seems to speed up as we get older. When you're young, everything is new, and your brain is constantly logging moments in crisp detail. As we age, we settle into routines. The days blend, and decades can seem to pass in a blink. It's not that time is going faster, it's that our brains are logging it. Perhaps the most potent shaper of psychological time is attention. When we pay close attention to time, we experience every tick of the clock. But when our attention is elsewhere, absorbed in music, reading, or conversation, time recedes into the background. This is closely related to mindfulness and meditation, practices that deliberately shift attention away from time. When we focus on the present moment, a breath, a sound, a sensation, time seems to dissolve. We stop measuring it and simply exist within it. Children, too, have their own unique relationship with time. For a young child, time is fluid and imprecise. Only as they grow and are introduced to clocks and schedules do they begin to align with adult time. And finally, there's anticipation. Looking forward to something can make time slow to a crawl, while dreading something can do the same. Our brain uses the same machinery to imagine the future as it does to recall the past, stretching time with hope and fear alike. So, is psychological time reliable? Not really. Is it logical? Often, no. But is it deeply human? Absolutely. We may live in a universe of ticking atoms, but the time we actually experience, the time that colors our lives, is woven from memories, emotions, attention, and imagination. It's time felt, not measured. And maybe that's why it feels so personal, so strange, so beautifully inconsistent. Let's be honest, no discussion of time is truly complete until we ask the question that has launched 1,000 stories. Can we travel through time? Well, maybe. But it's complicated. Time travel, at least in theory, isn't entirely forbidden by physics. According to Einstein's general relativity, the fabric of space-time is flexible. It can stretch, warp, and under the right, incredibly extreme circumstances, even loop back on itself. Let's start with the easy kind, traveling into the future. This one isn't just possible, it's already been done. Remember time dilation? If you move very fast, close to the speed of light, time slows down for you. If you were to travel in a spaceship at near light speed and then return, decades could have passed on Earth, while you'd only aged a few years. Congratulations, you've time traveled into the future. The practical problems, however, are monumental. We're not sure wormholes exist, and if they do, they would likely be unstable and require exotic forms of energy to keep open. So while it's fascinating on paper, building one is beyond our grasp. But even if we could travel back, we'd run into paradoxes. The most famous is the grandfather paradox. You go back in time and prevent your own grandfather from meeting your grandmother, thus preventing your own birth. But if you were never born, how did you go back in time to begin with? There are a few proposed solutions. One is the block universe model, where the timeline is fixed. You can go to the past, but you can't change it. Your presence there was always part of history. Another is the many worlds idea, where changing the past simply creates a new, branching timeline, leaving your original universe untouched. And a third idea suggests that the laws of physics themselves would simply prevent you from creating a paradox. Still, all of this remains theoretical. No one has ever documented a time traveler. If backward time travel were possible, where are all the tourists from the future? Perhaps it's simply impossible. And maybe that's for the best. Time's one-way nature is part of what makes our moments meaningful. We can't edit our lives, we simply move forward. Still, it's fun to dream. And who knows? Maybe someone from the future is listening to this right now, nodding quietly and thinking, "Ah yes, the primitive beginnings of temporal theory." After traveling through the physics of clocks and the psychology of minutes, we arrive at perhaps the strangest question of all. Does time actually exist? Now, that might sound like a philosopher's trick, but it's a question that physicists take seriously. Because when you peel back the layers, time starts to disappear. For most of us, time feels like a river, flowing from past to present to future. This is called presentism, the idea that only the present moment is real. But there's another idea, made famous by Einstein's theories, called eternalism. In this view, time doesn't flow at all. All moments, past, present, and future, already exist. The universe is a four-dimensional block. Time is a dimension we are part of, just like space. Your childhood, your future, and this very moment are all laid out like pages in a book. This idea arises from relativity. If two observers moving at different speeds can disagree on what now is, it suggests there is no universal present moment, which makes the idea of a flowing present a bit wobbly. And quantum gravity adds another twist. As we discovered, when you try to combine quantum physics with general relativity, but if time doesn't exist at the deepest level, why does it feel so real? One possible answer is emergence. Time, like temperature, may not be a fundamental ingredient, but something that arises from more basic relationships between things. The way we perceive motion in a film is just a sequence of still frames, but our minds create a flowing narrative. Perhaps time works the same way. What we perceive as the passage of time is really our brain stitching together changes in a fundamentally timeless reality. It's a radical idea, but it raises an interesting possibility. Maybe the sensation of time passing is a feature of our perception, not of physics. We are narrative creatures. We remember the past and anticipate the future. We measure time because it helps us organize our world. But that doesn't mean it's real in the way a rock is real. Still, not everyone agrees time is an illusion. Many physicists argue that even if time emerges from something deeper, it has real effects. Clocks tick, planets orbit, things decay. If a machine can consistently measure change and agrees with all the other machines, doesn't that make time real enough? Maybe that's the best answer. Time is real in the same way a story is real, not because you can hold it, but because it structures the way things happen. It's the script that allows events to make sense. So, does time exist? Perhaps not as a flowing river or a ticking clock, but it exists in our experience, our biology, our culture, and our equations. It exists in how we live and how we remember. It exists in every heartbeat and every bedtime story. And maybe that's enough. Because whether time is fundamental or emergent, real or imagined, it gives shape to our lives. It reminds us that moments are precious and that somewhere in the fabric of the universe, you are quite timeless here. And so, dear listener, we arrive at the end of our little voyage, or perhaps just another moment in the vast, quiet sea of them. We've wandered through ancient sundials and atomic clocks, ridden Einstein's warping waves, and stared down the question of whether time exists at all. Along the way, we've seen that time is not just one thing, but many, a rhythm felt in the body, a trick played by memory, a wrinkle in gravity, a story told by change. And now, here you are, a little farther along your own timeline than when we began. But was it minutes, an hour? Or did the flow of words stretch and shrink? And if you found any calm in this quiet expedition, if the wonders of the cosmos helped you drift gently toward your dreams, I hope you'll rest well. Time may be slippery and strange, but right now, here, in this moment, it's just you, this voice, and the slow, steady rhythm of rest. Sleep well, fellow traveler, wherever and whenever you are. See you tomorrow in next episode of The Midnight Scientists. Sleep well.